If energy is change, then measurement is the act of bringing order to that change. The earliest human tools for counting, notched bones, beads and marks on clay, were primitive attempts to measure cycles of time and motion. Today, our computers carry this legacy forward, converting energy into binary codes that can simulate galaxies, predict weather, or detect the faint signal of corrosion along a buried pipeline. Every measurement is both a snapshot of the present and a bridge to the future. Batteries are a practical example of this universal principle. They are controlled corrosion, metal electrodes reacting with electrolytes to release energy in a predictable way. The same laws that drain a battery also eat away at pipelines and structures if left unmeasured and uncontrolled. By studying batteries, we are not just learning how to store energy, but also how to understand the flow of electrons at its most fundamental level. The Alexander cell was born from this recognition that corrosion could not be managed by abstract potentials alone, but only by direct measurement of current at the corrosion cell. This step is as revolutionary in engineering as redshift was in cosmology. It turned theory into a measurable fact, transforming corrosion science from guesswork into precision. The DCVG survey added another layer, allowing engineers to map faults over entire networks of pipelines with clarity once thought to be impossible. What emerges is a unifying view of science, whether we are studying the universe or the failure of a pipe. The goal is the same: to trace the path of energy, to measure its flow, and to anticipate its consequences. The expansion of galaxies, the discharge of a capacitor, the rusting of iron, all are governed by the same relentless pursuit of equilibrium. In this sense, energy storage, batteries, corrosion, and even quantum theory are not separate fields, but chapters of one story, the story of transformation. Our task is not only to observe it, but to master the tools that allow us to guide it. With the Alexander cell, cathodic protection network blockchain, and new computational methods, we are writing the next chapter, where invisible currents become measurable, controllable, and ultimately the foundation for a sustainable future.